Right now, somewhere in the Pacific, a machine the size of a skyscraper is deliberately holding back its own power. It's a modern container ship nearly 400 meters long, carrying hundreds of millions of dollars in cargo. Its engine is as tall as a 4-story building, powerful enough to push the steel island across the ocean at more than 24 knots. But it's moving at 15. Nothing is broken. The weather is clear. The technology to go faster is already on board. The captain is under strict instructions not to speed up. That sounds backward because almost everything else in modern life has been built around speed. Messages cross oceans in seconds. Air cargo leaves Asia at night and lands in Europe by morning, yet the physical infrastructure that makes global trade possible is moving in the opposite direction. The largest moving objects ever built for commerce are being slowed down on purpose. To understand why, you have to leave the language of speed and enter the physical world the ship is actually moving through. A container ship moves through water, which is roughly 800 times denser than air. Every second, a vessel weighing more than 150,000 tons has to force huge volumes of water aside just to keep moving. As speed rises, resistance rises with it. Naval architects describe this with a rule that has brutal financial consequences. The power required to propel a ship rises roughly with the cube of its speed. Increase speed by 20% and you don't need 20% more power, you need roughly 70% more. Double the speed and the power requirement rises by about 8 times. Fuel already accounts for more than half of a ship's operating cost. A modest increase in speed can mean burning tens of extra tons of fuel every day for 2 or 3 weeks straight. A captain asking for more speed is asking the operator to pay for it hour after hour all the way across the Pacific. That alone explains why speed is expensive. It doesn't explain why the industry chose to slow down. For that you need 2008. During the early 2000s, China's manufacturing boom and surging Western demand pushed shipping lines to order larger, faster vessels. Then the financial crisis hit. Consumer spending collapsed, cargo demand weakened almost overnight, but shipyards in Korea and China kept delivering the ships ordered during the boom. The market was flooded with too many vessels chasing too little cargo while fuel prices stayed painfully high. Carriers were losing money on ships that had barely entered service. That's when the industry started pulling ships back. Vessels built for 24 knots were slowed to 21, then 18, sometimes 15. It became known as slow steaming, a survival tactic that ended up rewiring the economics of the entire business. Here's why. Imagine a shipping loop between Shanghai and Rotterdam. If a round trip takes 60 days, a carrier offering weekly departures needs about 9 ships rotating through that route. Slow the entire loop down, and the trip now takes 75 days. To keep the same weekly schedule, the carrier needs 2 more ships, even though cargo demand hasn't changed at all. It's similar to a city where every taxi starts driving 20% slower. The number of cars on the road stays the same, but fewer are available to pick up the next passenger. Effective supply shrinks. That's exactly what happened after 2008. Excess vessels flooding the market got absorbed into longer rotations. The industry found a way to burn less fuel while tightening capacity at the same time. And once capacity tightens, freight rates stop collapsing. A desperate response hardened into an operating model. The oversupply hadn't disappeared. Slowing the ships down had simply made part of it vanish from the market. Then came a second discovery, one that had nothing to do with fuel and everything to do with what was waiting at the other end. We tend to imagine global shipping as a race across open ocean. In reality, the ocean is often the easy part. The real bottleneck waits at the destination. A ship can cross the Pacific ahead of schedule and still end up anchored offshore with nothing to do. The berth occupied, the cranes busy, the yard already full. Arriving early creates no advantage. The ship waits, sometimes for days, burning fuel and tying up capital while expensive steel sits idle in the water. Once operators understood this, the logic flipped. If the port isn't ready, there's no point racing to get there. It's cheaper to slow down mid-voyage than to arrive early and wait. This is now built into shipping through just-in-time arrival systems. Operators adjust speed using satellite tracking, weather data, and live berth schedules. The goal isn't to arrive fast. It's to arrive exactly when the terminal is ready. This is the real inversion at the center of modern logistics. A slower ship isn't necessarily a less efficient one. The vessel moving at 18 knots may serve the network better than the one moving at 24, because it reaches port exactly when the crane, the truck, and the warehouse gate are ready to receive it. The ship isn't an isolated vehicle anymore. It's one moving part inside a much larger machine. Climate pressure now reinforces the same logic. Shipping produces roughly 3% of global greenhouse gas emissions, and cleaner fuels remain expensive and hard to scale. For many operators, the fastest available emissions cut is simply slowing down. Speed has become a liability on three balance sheets at once: fuel cost, market capacity, and carbon exposure. All three point in the same direction. So the world's biggest ships aren't sailing slowly because the industry fell behind. They're sailing slowly because fuel physics, freight markets, port congestion, and environmental pressure all converge on the same answer. The modern supply chain doesn't work because every part moves at maximum speed. It works because each part moves at the speed the whole system can actually absorb. Once you see that, the slow passage of the world's biggest ships stops looking like inefficiency. It starts to look like the hidden timing mechanism of modern civilization: steel hulls crossing open water not as fast as they can, but as precisely as the world behind them requires. Which raises a question worth sitting with. If the optimal speed for a ship is determined not by what the engine can do, but by what the port, the warehouse, and the factory on the other end are ready to receive, then the constraint was never really about the ocean at all. It was always about everything waiting on the shore.